In the cosmic wilderness between neutron stars and black holes lies a hypothetical wonder, the Quark star. Today, we'll explore these mysterious objects and their mind-bending properties. Every star tells a story. For massive stars, that story ends not with a whimper, but with a spectacular supernova, leaving behind something far stranger than ordinary matter. As stars collapse, they become incredibly dense. A neutron star compresses matter to incredible densities, but a quark star goes even further, breaking down the very building blocks of atoms. Inside a quark star, pressures are so extreme that even neutrons can't survive. Matter breaks down into a soup of quarks, the fundamental particles that make up protons and neutrons. Under extreme conditions, the boundaries between neutrons dissolve. What remains is a state of matter called strange quark matter, unlike anything we can create on Earth. This exotic form of matter is so dense that a teaspoon would weigh billions of tons, more than all the buildings on Earth combined. To understand this density, imagine compressing Mount Everest until it fits inside a sugar cube. That's still not as dense as quark star matter. These cosmic oddities might reveal themselves through gravitational waves, as their incredibly dense matter distorts the fabric of space-time itself. Studying quark stars could help us understand the early universe, when all matter existed as a primordial soup of quarks, similar to quark star matter. As we scan the cosmos for these elusive objects, each observation brings us closer to understanding how matter behaves at the most extreme conditions imaginable. Let's explore how extreme conditions can break down matter into its most fundamental components, revealing the strange world of quarks. At the heart of every atom lies a nucleus made of protons and neutrons. But these particles aren't truly fundamental. They're composed of even smaller entities called quarks. There are 6 flavors of quarks: up, down, charm, strange, top, and bottom. Each has unique properties that determine how they combine to form larger particles. Under extreme pressure, like that found in quark stars, atomic structures completely break down. The force is so intense that protons and neutrons can no longer maintain their form. The density of quark matter is mind-boggling. A teaspoon would weigh billions of tons. As the particles are squeezed incredibly close together, quarks interact through the strong nuclear force, mediated by particles called gluons. These interactions become crucial in understanding quark star behavior. As temperature and pressure increase, matter transitions through different states. Beyond plasma lies the quark-gluon plasma, where quarks roam freely. This extreme state of matter mirrors conditions in the early universe, just microseconds after the Big Bang, when everything existed as a soup of free quarks. The transformation from neutron star to quark star occurs when gravitational pressure overcomes the strong nuclear force, causing a dramatic collapse. Scientists study quark behavior using particle accelerators, smashing atoms together at nearly light speed to recreate these extreme conditions briefly. Let's explore the truly incredible physical properties of quark stars, where the laws of nature as we know them are pushed to their absolute limits. A single sugar cube of quark star material would weigh more than Mount Everest. This almost unimaginable density showcases just how extreme these objects are. Quark stars are about twice as dense as neutron stars, which are already so compressed that a teaspoon would weigh billions of tons. Despite their incredible mass, quark stars are tiny. A typical quark star might only be the size of a city, roughly 10 to 12 kilometers in diameter. Before we continue, if you're enjoying this journey through the extreme cosmos, consider subscribing to join our growing community of space enthusiasts. The surface temperature of a quark star could reach several trillion degrees Celsius, hot enough to break down any known form of matter instantly. The surface of a quark star would be perfectly smooth, as any roughness would be impossible at these densities. It would appear more like a liquid than a solid. The gravity at the surface would be so intense that light would bend significantly, creating multiple images of objects behind the star. Their magnetic fields could be 1 trillion times stronger than Earth's, powerful enough to tear apart atomic nuclei from a considerable distance. Inside, quarks would flow freely in a state called quark matter, similar to conditions that existed microseconds after the Big Bang. Now we embark on the most exciting part of our journey, the ongoing search for these elusive cosmic objects. Astronomers use powerful radio telescopes and observatories worldwide to search for objects that are too compact to be neutron stars, yet not quite massive enough to be black holes. Quark stars would occupy a unique position in size and mass between neutron stars and black holes, potentially filling a puzzling gap in our observations. One intriguing candidate is XTE J1739285, discovered in 2006. Its rapid rotation and unusual density profile have made it a prime suspect in the hunt for Quark stars. By plotting mass against radius, astronomers have identified several objects that don't quite fit the traditional models for either neutron stars or black holes. Gravitational wave detectors like LIGO could potentially identify quark star mergers, which would produce distinct signatures different from other cosmic collisions. Over the past 2 decades, several candidates have emerged. Each discovery has sparked intense debate in the scientific community about their true nature. The search continues as new technologies and observation methods are developed, allowing us to probe deeper into these mysterious objects. Multiple detection methods are used simultaneously: electromagnetic radiation analysis, gravitational wave detection, and neutrino observations. Future missions and advanced detectors planned for the next decade could finally provide definitive evidence of quark stars, resolving one of astronomy's greatest mysteries. As we conclude our journey through quark stars, let's explore how these remarkable objects connect to the bigger picture of our universe. Quark stars offer us a unique window into the conditions that existed mere microseconds after the Big Bang, when the entire universe was a super hot soup of quarks. By studying quark stars, we can better understand this crucial early phase of cosmic evolution, when matter as we know it hadn't yet formed. While particle accelerators can briefly recreate quark conditions, quark stars could serve as natural laboratories, sustaining these extreme states indefinitely. These stellar objects may help us understand how fundamental forces unify under extreme conditions, bringing us closer to a theory of everything. Future observations with advanced telescopes could confirm the existence of quark stars, revolutionizing our understanding of matter and the cosmos. Scientists are developing new ways to detect and identify quark stars, looking for unique signatures in electromagnetic and gravitational wave data. International collaboration and cutting-edge technology continue to push the boundaries of our knowledge about these enigmatic stellar objects. Many questions remain unanswered. How common are quark stars? What role do they play in stellar evolution? Could they help explain dark matter? Subscribe for more cosmic explorations and share your thoughts below. Together we can unravel the mysteries of these fascinating stellar objects.